afternoon. So I'm the secret speaker here. My name is Heiko Wolf from PSI Metals. PSI Metals is the leading supplier of production management solutions for the steel and aluminum industries. So we do everything to optimize production processes with solutions for planning, production tracking, quality, logistics, everything you need in a steel plant for the whole process, from the liquid phase all the way to finished product. So this is what we do. And I'm very thankful to Professor Landgraf and to Mr. Saito for inviting me to speak here to this great audience. And it also gives me the chance to, for the first time, visit this beautiful country and be with my colleagues here from PSI Metals Brazil that serve the local market. So as I said, at PSI, we deliver digital solutions, production management solutions for the metals industries. And with this, we are, of course, at the forefront of Industry 4.0 digital transformation. And it's a revolution, an industrial revolution. And like every revolution, there are violent changes. Things get thrown over, things get replaced. And so we hear about a lot of new things, a lot of technologies that want to replace the way things were done in the past. And Professor Landgraf stated it in his introduction. Who do we still need? What knowledge do we still need? And of course, we face this as well. Who needs production management systems? You could just upload all the data to the cloud, store it in the blockchain, or just have it in the smart slab. Why do you need a centralized system? And there is some truth to all these statements. There is a lot of new technology that adds value. But to really judge what we should do with this and what we should use, I think we need to take a step back and look back at the fundamentals. And they're really simple. The drivers for implementing IT systems in the metals industry: higher revenue, lower cost, of course. These are two core drivers, they will remain. And a recent report on Industry 4.0 adoption in Europe stated that one of the main reasons that companies are not adopting Industry 4.0 is because it needs to pay back its cost. I think that's just natural, and it should be this way. We shouldn't just implement it for the technology's sake. There are some other factors. We want to, of course, have high customer satisfaction. We want to have stable processes. And really important, we heard before, we need skilled, motivated employees. So we also need to have solutions that motivate our employees. And there is a whole toolbox available, of course, in the IT solutions for the metals industry. Increased automation rate, a seamless integration of all systems. And this involves, of course, also the Internet of Things and the industrial internet. Giving holistic process visibility and control and adding value through data. Also very important tools that I will speak about in the later part of the presentation. And last not least, high solution usability and context-sensitive decision support are the tools that help us support our employees and to upskill them to the tasks for the future. And to protect your investment and to simplify your production, of course, a product-driven approach, a rollout of a system over multiple plants is a big enabler as well. And so, as I said, PSI Metals, our mission is to increase the competitiveness of our customers with our offering, with our integrated system, and with all the services, with education, with training, with consulting for our customers. I said before, there are some hypes in the Industry 4.0 sector, but of course there's also a lot of value there. And we have been thinking, what is the main factor, the main added value that we see from this digital transformation? And for us, it is all about the connections and the network effects. And I think it mirrors nicely also the presentation from Gerdau that we heard yesterday here, that the structures of companies are changing, the hierarchies are going away, and it is all about connections between people, between systems, and this is on all the levels. And it starts at the lowest level, of course, connecting sensors and data. You need to collect the data and not let it lie in silos of systems in the automation or even throw it away, as we heard before. On the next level, we have the connection of systems. This is what our core business is at Metals, that we connect the systems along the production chain in our customers' plants. Connecting workers, very important as well, thank you. Connecting workers, connecting them to the data to make the right decision, and connecting them with the right devices. So here we see usage of new devices like mobile phones, tablets, data goggles, or audio control like Alexa, or new user interfaces like chatbots. We still think the worker, even if we have reduced worker capacity in steel plants in the future, the worker is the most important person in the plant, and we need to enable them to do their job in the best way. And last not least, on the highest level, we're also talking about connection of whole businesses and organizations. And here we mean, on the one hand, multiple plants, tracking of material through multiple plants, but also tracking to outside processing back into the supply chain of a manufacturer, and even incorporating the customer of a metals manufacturer. So to enable, for example, a car manufacturer to see into the production, where's my order, when is it ready, how can I influence the production, maybe get a cheaper price by getting a later delivery. So also some really interesting new business opportunities and new products can be developed on this level. And one thing that is very important and that we see as crucial here is that these services, these different parts, these new technologies, these new features will be delivered by all sorts of players. And again, I can refer back to the Gerdau presentation from yesterday. It's about what all of us do together and can achieve together. To run a successful production, you need a strong team. You need the best data analytics algorithms, you need the best automation, you need the best services for each purpose. But of course, in such a strong team, you also need someone who guides this team towards a common goal, who has the holistic process knowledge. And we think that these centralized systems that keep the process together, that tie in all the data from level 1, level 2, and all these new services have a very relevant place as the captain of such a team of services in Industry 4.0. So let me get to the topic of the second half of this presentation. How does data change what we do? What added value do we get from data in Industry 4.0? And of course, we saw it before in the previous presentations, we have to collect the data, we have to manage the data, we have lots of new technology for this, we have databases that can hold terabytes, we have techniques to store it in the cloud. And so this is all available, all this data that we collect from sensors. And the goal, of course, is not just to have it, but to make it available to give new functionalities such as decision support services or predictive services. But it is the basis. We have to collect it in the first place. And one thing that we found when we looked at this problem is it's also not a completely new problem for us. Data-driven process control has been around, again, for years. And we have this, of course, also in our system. What you see here is the statistical process control by tracking a parameter in a control chart. So up here, you see a control chart, a parameter is tracked over time or over the length of a material. And if a threshold is violated, then we can trigger an action. We can have configurable rules, as we saw before as well. We can inform an operator. And this is a very good way to control processes based on data. An example where we do this is the quality control at the vacuum degasser, where we measure the time that the pressure needs to build in the degasser. And if this time exceeds a certain threshold, then we can inform an operator and we can trigger some maintenance. This can also be used in the tracking of raw materials, where we can track the trend, for example, of the amount of aluminum in the raw materials. And then we can, again, if a certain threshold is violated, trigger some activity and inform an operator. And this enables to early on stop any problems that might occur if we ignore this trend. A third example, also similar from finishing, is when in an annealing furnace we can also again track the gas pressure, and here we can find out if maintenance of the nozzles is required. So this statistical process control is already a big step towards the total quality control. We have thousands of process parameters in our system, so we track them, we get them from the level 2 systems, and we track them along the material. The interesting part is here, of course, that we know from the material genealogy where a coil originated. We know from which heat the slab was generated and from which slab the coil was generated, and we can exactly project backwards where a defect that we could find on the coil originated on the slab. And this information, tracking of the parameters with this material genealogy, is already a very powerful tool to enable expert decisions. So to create rework, to make process adaptations. This way of doing things has its limitations though. These control charts usually track one parameter. If you have a host of parameters to look at, you need an expert to really analyze them and make a decision. And this is exactly where we see the huge potential for artificial intelligence modeling. When we have exactly this need to correlate many, many different parameters with a certain outcome. And here we just see 3 parameters measured along the length of a material. But how do you judge now that if one of the parameters has a high output to the top or to the bottom, whether that already consists a problem, or maybe in correlation with the other parameters, it's actually okay. So this is hard to judge just by simply looking at it from an expert perspective. And this is where we see these AI models coming into play. An example of how much data we collect is this example production process from a cold rolling mill. So from hot strip to cold strip to finished and to semi-finished and finished product. And along this production process, we collect 4 types of parameters, data points. The first one are the defect measurements. So by some tests, we have found out that the defect is occurred on the material and we know exactly its location. And so we can use this data point. Secondly, from some production process steps, we also have the process measurements along the length of the material. So for example, temperatures, pressure, all these data points we can also collect and use. Testing from sample taking, where we analyze a piece of the material, of course also an important data point. And even these statistical process control charts. The output of such analysis also becomes a data point that we can then use again in further analysis. So lots of different types of data that we collect along the whole production process. And here on this slide, I just want to point out the right-hand side. The important part for us is here that any machine learning algorithm, any big data technology, these are very generic tools that can be used in many different fields. But what makes it valuable for us is putting it into the process context and putting it into the context of the domain know-how. And this on both sides of the equation. So one side is the input side. You saw the many parameters we collect. So to judge which are actually reasonable, which are actually valuable to put into your model. And then again, on the output side, what do you do with the output? It's often not a black and white decision, but more or less a likelihood. If you go this way, defect may occur with 60% reliability. And this is where we need the expert know-how to judge. We at PSI Metals, we're part of a larger software group, the PSI Software AG. We have sister companies in many industries, manufacturing, logistics, mining, road management. And in this cooperation, of course, we share these artificial intelligence approaches as they are very generic. And I just brought 3 examples here as how these very generic approaches are made usable for specific industries. The first one is an example from manufacturing, and here it's about fault detection in tires. So we can use image recognition, we can train a neural network on image of tires, and we can relate these image data to defects that had later occurred on the tires. And now we have there an almost completely automated quality assurance system that can trigger a warning if a defect can be predicted. The same automation and high throughput screening is achieved on the second example. This is our luggage tracking from our airport system. And here we also use a neural network trained on image data to track luggage pieces through the airport and to find out where they maybe were damaged in this process. And again, it leads to high automation and much faster processing of problems in the process. And then we have the third example, and completely different field. Here we're using a neural network to predict the state of a road in the future. So we predict if a road may become icy or wet, and this is used to predict the travel times for the next 36 hours. This project is actually implemented in Norway by the Norwegian Transport Authority, and there they use it to check whether the roads are good enough to get the salmon in time to the airport. So it's very important for their industry. And the underlying technique, the underlying technology is very similar in all the cases. And of course, we're learning from each other, from other industries, and see how we can apply these technologies to our own industry. One example where we are applying this technology is for routing decisions and quality predictions in rolling. So here you have a sample environment in which we have to decide on which route we should produce a material. We have 2 hot mills, we have some pickling lines, some cold mills, and so on. And our system already has the knowledge to support the decision where it should be routed to produce the right quality, what is the line capable of. It takes into consideration in the planning what's the current load of the line. There might be also transport distances to consider. So this already gives a very good decision of where to route the material. What it doesn't take into consideration, though, at the moment is what is currently going on in the plant, what is the current maintenance state of the lines. This may impact the output quality. Also, it does not take into consideration what happened in the past. Of course, experts can know this and can make the changes to the quality decisions, but the system doesn't know that on a given route we always had the problem with this defect and takes it into consideration. So we have all this data, but we're not using it yet, and this is where our quality prediction comes in. So for this quality prediction, we first of all have, of course, the real-time production data. So we track with our production and quality module all the actual process data from the process and the material quality data. At the same time, we of course have a wealth of historic data. We have the whole process data archive available where we tracked all this process and quality data. And in both cases, we have always the material genealogy available to project data back and forward along the production process. And so what we now did is we used this process data archive to build a model that relates the input parameters, the quality parameters, and the process parameters to the given output on a given route. And of course, then we want to use this model in production. We want to feed it with the current data. We want to feed it with the possible routes. Of course, not every route is possible. And get back a quality prediction for every route. So this was the setup that we wanted to implement. And the idea here is that we have the measurements after the hot rolling. So we have surface inspections and we have certain defects there. And we also know about the process parameters that happened throughout the hot rolling. And of course, we know the process parameters of the following production steps. And by building this into a model, we are then enabled to request the likelihood of a defect from the online model. So what we do is, after the hot rolling, we will say these are the quality measurements after hot rolling, and this is the state of the future lines, and we will receive a likelihood per defect per route. So it's not, as I said, a black and white decision, but we get, for example, pickling 1 would yield to a defect A likelihood of 80%. If I go to pickling 2, it might only be 30%. And now I have to, of course, judge what is the cost that this defect brings me to decide what is the best action to go forward here. So we're implementing this with the customer at the moment. And of course, when you're implementing this, you hit the reality and then you see what adjustments you have to make in your approach. So some first project results. The initial idea to give route predictions is actually quite difficult to pursue because there's actually not enough diverse training data. Generally, it's always the same route that is used for a given product. So we can predict, of course, but we will have only enough data to reliably predict it for one route. And so we moved a step back and thought about what can we do with this setup? Where can we add value for our customer? And it's still very similar. We moved now to the defect prediction after the hot strip mill. And there we found there are 3 types of defects that can occur. There are first the defects that happen at the hot strip mill and they can be detected right after. No prediction necessary. They are detected directly by the tests done in the plant. Second group is the defects that occur at a later line, at some finishing line, and that are also detected directly there. Another group where we have nothing to predict. The interesting point comes down here in the red box. Defects that happen at the hot strip mill but are only detected much later. So then there can be other problems can have happened because we didn't treat the defect, we wasted production resources on something that we cannot sell. So here's real value if we detect or predict directly after the hot strip mill that something needs to be done about this defect, some rerouting, some rework. And this is what we're focusing on. So we have some promising detection results, we still have some issues. So with the current model that we built, that includes these blue boxes down here, we still have a very high rate of false positives that we have to work on. We have some proposed actions to remedy these problems, and one is, for example, adding new variables. This is what I mean. We talk to the experts, we look at the data, and we think about new variables that we can add to the model. So we're now thinking about adding also equipment data, adding shift data, or even adding the weather as data into our model. The second point is also to increase the granularity of the data in the model. So far, we have been using the processing logs of the hot strip mill in an aggregated way, and now we're looking at using the raw log data. So this is one approach. And then also we're looking at increasing the time, so we have even more training data for a longer time period. And then there's still the question of how to handle it in a productive setting, where we're discussing with our customer what actions can actually be performed and how can we relate the cost of the defect to the cost of the action to be taken. So what you see here is you have a model that you can train, that you can build, that gives you some output, but it will require the local expert knowledge to put it into context, to understand what this output means, and then to also react to it in production. So in summary, we have already a lot in the systems that we have. So in production management systems, also in a lot of level 2 systems, we store all the quality data, we store the process data, we have the material genealogy, and we can project it backward and forward. And this is a very good base for expert decisions already today. But artificial intelligence modeling really adds another nice tool to our toolbox. When we get to a point where we have to correlate many input parameters, maybe sometimes even don't know which parameter really plays the main role, and we have to try out different combinations, then this can really unfold its power. It can speed up the decision making, which is a very important point, and it can even enable us to handle previously unknown situations, because the model will try to correlate that with the knowledge that it acquired in the past. So a very nice tool to expand the toolbox, but to echo my previous speakers, it doesn't replace what we had before. It's another addition to us that will make us even better in the future. So thank you for your attention.